Hello everyone, we're the virtual ROS-based self-driving car model team. My name is Victor Abril. My teammates are Nathan Yu and Shuna Rangwala. The project that we worked on for the past summer is part of a bigger project that focuses on developing a virtual city environment simulator. In our project, we focus on developing the self-driving cars. We incorporated ROS to control the car models in the virtual city environment, and also use machine learning algorithms to create the self-driving car model. As you can see on that picture, we use a Prius model to as our basic car model to develop the self-driving car. It had many different sensors, but out of all these sensors, we only used the front camera to develop the self-driving algorithm. I previously mentioned that we're using ROS, but which stands for Robot Operating System. But what exactly is ROS? Well, ROS is basically a framework on top of the operating system that allows us to code hardware components of a robot by just using software. This implies that we can create programs for robots without having to deal with their hardware. In this example, I developed of how a typical environment in ROS looks like. Um, when you program in ROS, it usually encourages you to separate your code out into different components that each do one thing. Each program that you write that does this specific task is called a node. In this specific example, we have three nodes. Node 1 is a script that reads the odometer in the robot's wheel and tells you where the robot is relative to where it started from. Node 2 is a script, which is a path planner that tells you how to get from point A to point B. Node 3 is a code that, given the velocity command, tells the motors to move in a certain way to achieve a certain velocity. The way in which these nodes communicate with each other is through topic. A topic is kind of like a named channel that nodes can send data into other nodes. So in this specific example, you see that node 1 communicates with node 2 through topic 1 of name autumn. And node 2 communicates with node 3 on topic 2, which is named CMD-val. Now, the data that actually gets sent to the topics are called messages. As you can see, node 1 sends XYZ position coordinates to node 2, which is the path planner. And then the path planner can send data to the motor controller to, for example, telling it to move forward 0.02 units and not turn it off.
So now I'm going to talk to you about why we needed this data and how we went about collecting the data. So in order to train our model, it needed to learn how to drive using the camera images and steering wheel positions as data. And the more data that this model studies, the better the model could drive itself. And to do this, we recorded ourselves driving the Prius model in the simulation, and we stored the steering and image topic data in files called bag files, which is a ROS built-in for collection. And if you see at the bottom left is our general setup where we see the front camera and the simulation. And the bottom right is us cropping the images we got as data so that it fits the model's input.
Okay, I'll explain to you about the deep learning neural network that we used in our model. So as Nathan mentioned, we require the front camera input, which is the image. We actually designed a loader data class, which would randomly sample through our data set and get those images and train the model on those images. We did this because this would like boost our space complexity, it would lower it and make it easier for us to use. What the model does is it takes in the input of the image, processes it, and gives it a float value, which is between 1 and -1. This is the steering value, which will control how much the car should turn left or right. So our self-driving implementation includes two additional nodes. One is the predictor and one is the drive node. The predictor node has the model which we coded and evaluated beforehand. It has it initialized in it. So when the front camera sends through the topic an image, into the predictor node. The model inside the predictor node will evaluate the image, generate the steering output, and pass it to the drive node, which in turn would compute the control message, which drives the car around our cityscape. Now Nathan can explain the results that we obtained after training our model.
Okay, so on the left, we have our training video after 10 training cycles and 15 bag files, relatively medium size of data. And as you can see, the car is following the path pretty slowly, but it's still following the path. It's pretty slow and it's exhibiting a wobbling behavior going left and right. So after we trained it using a lot more data and for longer, using 20 training cycles with 37 bag files, we see that the car on the right is driving a lot smoother and following the path a lot better than on the left. So this is evident that with more training, the model itself was able to learn and even predict better training paths than we created in our recordings. And that's it. Thank you.